excited to see everyone here in Amsterdam. This is kind of a home game for me. So I'm not from Polygon yet. I'm from WorldCoin. We're working on the proof of personhood problem. So one of the things holding back DAOs and airdrops and a lot of things in Ethereum right now is not being able to do things for a single human being. There's always this risk of being Sybil attacked. We're solving that after exhausting every other option. We came to biometrics as being the only viable way to onboard the entire planet, which, as you are probably aware, is over 1 billion people. And we want to do this disconnecting people's biometrics, which are obviously privacy invasive, from what they end up doing on the blockchain. Hence, anonymity for 1 billion people. So I want to start with giving a brief overview of the history of anonymity, because I was digging into it recently and I thought it was kind of interesting how this concept has been evolving within cryptography. And then I'll go and explain the Semaphore project, which provides anonymity on its own, which is actually a really novel concept. And then I'll show what sort of issues you get when you try to use Semaphore at that scale, and what we are going to try to mitigate that. So the history of anonymity, the cryptography has been mostly interested in, like, how do we make sure this message is actually from someone and not the opposite. As far as I'm aware, it only started in '82 with David Chaum's first eCash paper, where he introduced blind signatures. Blind signatures allow you to basically go to the bank, prove to the bank that you are who you are, and then the bank will stamp your transaction but not be able to know the transaction, and you can submit it then. Which requires a trusted party. This signature-based approach got like another interesting component with in 2001 with ring signatures, which allow you to sign a message using a member of a set without revealing whom of the set it is. And then in 2014, CryptoNode added the concept of stealth addresses there, where you can kind of hide your public key but still allow people to, like, you would no longer be able to connect a signature to a particular public key. And this work ended up in Monero, which uses all of these tricks together in order to create a completely private cryptocurrency that actually doesn't use, or at least in its initial version, didn't use any zero-knowledge proofs. It was just based on elliptic curve signatures. Aztec was the first application of these technologies in Ethereum. Since then, they've used zero-knowledge proofs, and actually back then they also used zero-knowledge proofs for different things, but since then they've used different schemes. I just wanted to mention because they're the first ones to use it on Ethereum, and also the first ones to provide anonymity of that kind in Ethereum. That's one line of history, and then there is a completely separate line of history of the cryptography of anonymity that is around zero-knowledge proofs, which started in 2013 with the Zero Coin paper. This is the construction I will explain in detail later, so I won't go into it here, but that evolved into Zero Cash. The Zero Coin paper used a vector commitment scheme based on RSA, which is kind of clunky and complicated. The Zero Cash paper turned that into a Merkle tree, which we all know and love. And then Zcash turned this into a ready-to-use product. We again see the transition from white papers to logos. Tornado took a very similar construction and put it on Ethereum first. And then almost simultaneously, and by the same people that built Tornado Cash, they realized that, hey, we can actually abstract away all of this transferring funds stuff and just provide anonymity on its own as a ready-to-use primitive. And I found it so interesting that this idea has not come up before. Like, up until now, the idea of anonymity was always closely tied to transferring funds. And there were always two aspects to it. Like, how do you keep the identity of the participants secret? And how do you keep the amounts transferred private? All of the research and all of the struggles that have happened were around keeping the amounts private. Keeping the identity secret was actually the easy part, and it was pretty much solved in its current form in the 2013 paper already. So it's kind of funny how long it took for people to realize, let's just unbundle these two problems and take the solved one and provide it as a primitive. But we have that now, Semaphore. Open source project done by Applied CKP from the Ethereum Foundation. I recommend everyone to check it out. And it basically does this. So you have a set of users in your system called the Anonymity set. And then you want to allow these people that are in your system to make a certain kind of a claim. The specific nature of the claim depends on what you're trying to build. For example, in the case of Tornado Cash, you want to be able to claim that, anonymously claim that you were one of the people that put money into the system so that you can take it out later. In general, these claims have three important parts to them. The first one's obvious. You need to be a member of this set. You need to be a member of the people allowed to vote in this DAO. You need to be a member of the people who put in money in this mixer. You also need a one-shot requirement in there. You need to show that I haven't taken my money out of this mixer before, or I haven't voted on this particular proposal before. You'll notice here that there's a bit of context involved, like it's specific to a particular voting proposal. Semaphore solves this in an elegant way that we'll get to. And then in the case of voting, there's also a signal component to it. You also want to provide a message. You want to say if you vote for or against the proposal. So if you have these three components in a zero-knowledge claim, you basically have your anonymizing primitive that you can use for all applications where you would need such a construction. We're getting really technical here. So how does this work in the case of Semaphore? I have two pieces of pseudocode here. The Python-esque one is what happens in the zero-knowledge proof on the user side. This is a proof that they're computing on their phones or laptops, basically in their wallets. And then we have the contract, the Semaphore contract on the right. So the Semaphore contract has a root in it, which is the Merkle root of all the members in this anonymity set. And then it has a mapping from uint to bool called nullifiers, which is a way to remember who has already made a claim and who has not yet made a claim yet. Now, what does a claim look like? In a claim, we have three inputs, basically. The user provides the signal, which is, for example, the vote that they want to cast. You take the root, the Merkle root of the tree of all the anonymous set. And then you have this external nullifier, which basically acts like a salt or a domain separator, or however you want to call it. It's something unique to what we're currently claiming on. It represents the context. It could, for example, be the idea of the proposal you're voting on. And then you have some private inputs. You have a private key in this system, and you'll provide the Merkle proof as a private input just for efficiency's sake. Now, the way the membership is proven is very simple. That's just a straightforward Merkle proof of the hash of your private key. In this case, we can just take the hash of the private key as a public key. The assumption is that before you've inserted your identity in this Merkle tree. So that's the membership part of it verified. Now, the interesting thing, and the thing that you really need to wrap your head around the first time you see it, is how the one-shot is implemented. What you basically do is you take part of the private key, hash it with the external nullifier, and this creates a number that is unique to you, because it contains some of your private key in it, and it's also unique to the current context. And that number is your nullifier, which will be made public in the process. In some sense, this kind of violates your anonymity because you're now assigned a unique number. And indeed, if you try to create the claim again, you'll end up with the same number, and we know it was you. But this is our goal here. We want to prevent people from doing it twice. If you only do it once, all you see is basically a random number, and you don't have any way to link it to any of the other random numbers that happened in the previous voting rounds or in future voting rounds, so it's still completely unlinked. You only lose your anonymity as soon as you try to do something twice that you shouldn't be doing twice, and that is what provides the one-shot mechanism here. And then finally, the signal is kind of simple. It's just hashed into the proof in a way that, yes, it was proven against this signal. It's not even actually used there. And then in order to verify such a claim, you just check that the proof itself is valid. In the case of Semaphore, that's currently a GROT 16 system. You check that the root matches the current root. You need to be a little bit careful that if you keep adding and removing members and the root changes over time, you get some concurrency issues, but that's all solvable. You need to make sure that the external nullifier is valid for what you're currently trying to run a round of proofs over. And then you need to maintain some state. You need to make sure that you haven't seen this particular nullifier before, and then you need to set the state to true so that you will prevent this user from voting again. And then you can emit a signal or do whatever you want to do, deposit a token from an airdrop, withdraw funds. So that's the verification function. Now, adding a person in the current Semaphore architecture goes like this. You create two random numbers. Your private key just happens to be two random numbers. You compute the Poseidon hash of them. Poseidon is a zero-knowledge efficient hash. And then you just call the contract and you say insert identity. Often there will be more logic involved to the specific use case. For example, in the case of WorldCoin, we also want you to do a biometric verification to make sure that someone with your biometrics hasn't signed up before. Once that check has passed, you insert the identity. Currently, that works by updating the Merkle tree in Solidity in EVM. You update the root hash, you move to the next leaf, and so on. So now you have this Merkle tree on-chain with the root updated, you have these verification functions, and we have our basic primitives for adding users to the anonymity set and them using the anonymity set. Now, this has limitations, this design, if you want to scale it to 1 billion users. If you want 1 billion users, you need at least a depth 30 tree, and that tree will have a size of 32 gigabytes. This, fortunately, doesn't need to be stored on-chain. That will be completely impossible. But if you remember, in order to create a claim, you need to know the Merkle proof. So if you have this contract, let's say you're like the 900 millionth user to insert your public key into the system, now you need to go through the blockchain. You need to download all the insert user events so that you know the entire Merkle tree so that you can compute your own Merkle inclusion proof. Basically, in order to get your Merkle inclusion proof out of the system, your only option is to download the entire tree from the log events and reconstruct it locally. This is simply not mobile friendly. We cannot expect our user wallets to download 32 gigabytes of data. So that's one thing we'll need to solve. The second thing is that the on-chain updating of the Merkle tree is quite expensive. It's 2.5 million gas. For certain applications, this is entirely feasible. For ours, it isn't, because to sign up 1 billion users, we would have to spend about $300 billion. That's simply not going to work. The other thing that could be improved is that the verification, even though it uses GROT 16, which is super cheap and efficient, it is still 300,000 gas, which is in the order of $100. So if we're talking about doing an airdrop that is worth in the order of tens of dollars, then it's just not cost effective to do it through a mechanism like this. And we do want to use anonymization mechanisms. It also wouldn't work for an application like on-chain voting. If you put up an expensive hurdle like this in your voting process, it will likely affect the participation rate. So what can we do there? Well, we're at the L2 event, so we'll introduce a sequencer and an aggregator in the process. One easy thing you can do, in fact something we've already done, is provide a central service that gives you the Merkle proof. Like you add yourself to the tree. We have a server running in AWS somewhere that constantly monitors the contract for events and keeps an up-to-date tree in memory, and you can just call the API, it will return you your Merkle proof. It's kind of a light client because you can verify the Merkle proof locally and match it against the contract route, so there's no trust involved to this server. However, in the process, this server does learn your IP address if you're not using any anonymization services there, which is a slight de-anonymization risk, because now we can tie your public identity and so your public key and therefore your iris hash or whatever mechanism you use to sign up to your IP address, which is undesirable. So for that, we have actually been looking into something called private information retrieval. I'm assuming most people haven't heard of that, but zero-knowledge proofs are, I would say, one example of like a class of advanced cryptography that is out there, and other examples are like homomorphic encryption, multi-party computation, and private information retrieval is one of them, where it's a cryptographic mechanism that allows you to query a database without the database learning what your query was. And much like zero-knowledge proofs, it's been going through some slow advances. Academically, it has like gigantic key sizes, but it actually is hitting the point where it could have its first applications, and this could be a good one, because it solves a true anonymity problem. And Merkle trees are fairly static and all this, so it's easy to pre-compute expensive things. So that's one thing that's out there. The second thing we can do is, instead of recomputing or updating the Merkle tree on-chain, we can use computational integrity proofs here, basically zero-knowledge proofs to insert these members. That should give a 10x improvement already. Then if we, but this fundamentally requires a sequencer, because now if you have two concurrent insert operations, they don't know the sibling tree node hash values yet. By introducing a sequencer in it, you now have a guaranteed slot in your tree. You can process them in order, so you do know all the neighboring slots, and suddenly you can actually use zero-knowledge proofs to make this cheaper. But if you already go through this length, why not insert an entire subtree at a time? And you get to aggregate insertions to further amortize the cost of insertions. Then that kind of solves the expenses of the insert operation, which can now be sublinear if you implement all of this. Then we have the nullifiers in the verification, which is currently in storage, which is storage is expensive and it scales linearly with the number of users, number of claims made. So one thing you can do there is store them instead in a sparse Merkle tree, and also update that using a computational integrity proof. Again, that requires a sequencer, because you need to know your sibling Merkle tree values. And then the final thing is you can aggregate the proofs of the claims themselves, which will require a recursive proof system. And this is where we come into where things come back to Polygon, like they have consistently this morning. They developed, like you've heard several times now, a really cool recursive proof system. So switching semaphore to a recursive proof system would allow us to aggregate multiple claims, and then we can also amortize the cost of making a claim in a DAO or an airdrop to be sublinear. So that's what we're currently working on. We have the sequencer, like the semaphore sequencer service, open source already, but currently it only implements the API for fetching the Merkle proofs. We'll be working a lot more on this going forward. definitely check out the Semaphore project. We'll do a workshop on Saturday where you can play with an SDK and build your own airdrop on top of our anonymity set of all humans. And I'll be talking more about the project and how the orb works and the iris hashes and other interesting things to make sure that privacy is preserved on Saturday. Thank you all for your time, and are there any questions?
Thank you, Remco. Any questions? Any immediate questions from the audience? So maybe let me start with one. Considering that all this work is done in the context of the WorldCoin, I find it personally quite ironic that people are like afraid of the privacy, and yet at the same time, what I'm seeing here is just mind-blowing complex cryptography, and the advances that are just simply there to protect the privacy, right, and anonymity. So how do we actually convince these billions of people to trust the math?
I mean, how do you convince billions of people to trust elliptic curve cryptography? I would say that most people using TLS and digital signatures don't really know how they work in detail as well. And kind of the funny thing is that with zero-knowledge proofs, you have this really clear abstraction. Like the underlying math is super complex, but then you get this sort of API abstraction SDK layer on top that is very elegant and simple, much like you don't need to learn elliptic curve cryptography in order to understand like the dynamic of groups. And you don't need to understand all this group math in order to understand what digital signature is. So there are these clear abstraction boundaries in there, and then as long as like everyone can, depending on their level of curiosity, go however many levels deep into the math as they need to convince themselves that things are sound. Having lots of experts like here in the audience out there vowing for the integrity of the various constructions that we're using also helps, because in the end, the people who don't really want to dig into all this math, which I personally can't understand, but they seem to exist, they can rely on experts to do that for them, and yeah.
I guess it's all about building trust, right, to the whole system. Any questions from the audience?
Hi. Oh, that's working. You mentioned that there is a way to solve Merkle tree update using zkPay, and so there is an issue with it with race conditions, right? And you mentioned that it can be solved by sequencer, but it looks like it's a centralization point, right, in this scheme.
It is a centralization point, and it is subject to the same, I would say, relatively mild concerns that L2s are, in the sense that there is no option for this operator to do anything malicious, but you do have a censorship risk that you introduced in the system now. You can probably do standard escalate to L1 techniques to mitigate that if you needed to. But yes, introducing sequences always creates some form of censorship risk that you need to address.
Any more questions? Okay, no more questions, so thank you very much.